Hello.
Hello?
Yeah, yes, Sir Penrose. I mean, you can hear us?
Can you
Hello?
hear me?
Yeah, yes, we can hear you. We can hear you.
Yes.
So we'll just start in 5 odd minutes. So thank you very much.
It seems as though I'm not low enough now.
Hello?
Hello?
Yes. Are they talking to
I
you?
think we have contact, and I'm not quite sure what's going on.
There we are.
Well, thank you. That's great. Is that? I can't see my image very well. Is it all right there? And the talk somewhere, where is it? You can do that. And which way do I do the clicking?
Everybody went to class.
Hello. 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 I mean, Sir Penrose, we cannot hear you as of now. Okay.
Hello, can you hear us now?
Oh, yes, we can. We can.
Ah, great. Okay.
Thank you. Thank
That we have to get my talk.
you. We are just going to start in 2 minutes.
Okay, I'm just going to share the screen
Sure.
and Roger's talk. Oh, send request.
Oh,
I need you to turn on the sharing thing. You should have had a request so that
yes,
I
sure.
can.
Yes, sure. We are just about to
Thank
do.
you so much.
Thank you.
Oh.
Okay. I mean, just a few minutes. I mean, just in a few minutes.
Oh.
I mean, okay. I mean, please just wait for a few minutes. We are just going to.
Sure,
do.
yes.
Okay.
Screen.
Okay. Yeah. So it is done. Can you please try to share?
Sure.
मेरे इसमें नहीं हो सकता.
Yes, I can share. Okay. Yeah. So Right. There we are.
I should have
Okay.
a license on.
I think they'll tell you when they're ready.
Okay.
Just check. Yes, these two.
Okay. And
Okay, so I think we are not going to start.
which way do I move the slide? That's the other thing. Is it up and down? Because
No,
that
no. It's
it's,
there we are,
it
look.
is right and left.
yes. 1, 2.
Okay, I'll try and remember that. Not
Well, I'm
forget it
here.
in the middle of the talk.
Don't worry, I'm here.
Okay, so now we are going to start. So, good afternoon and good morning to our speakers, Sir Penrose.
Hello.
It is a privilege to have. It is a privilege to have a very distinguished speaker, Nobel laureate Sir Roger Penrose, to celebrate International Year of Quantum Science and Technology at TCG Crest, Kolkata, India. As the Twitter handle of Sir Penrose states, he is interested in cosmos, computation, and consciousness, and interconnections. He is best known for his work on gravitational collapse, which leads to singularities. He has been awarded Nobel Prize, Wolf Prize, Royal Medal, and many other awards. To a general audience, he is known for many books, such as The Road to Reality, The Emperor's New Mind, and Shadows of the Mind. Sir Penrose is also known for his theory of consciousness, the role of wave function collapse in the functioning of brain. Hello. Okay. So to a general audience, Sir Penrose is known for his many books, like The Emperor's New Mind, The Road to Reality, and Shadows of the Mind. He's also known for his theory of consciousness, the role of wave function collapse in the functioning of brain, and why computer cannot simulate intelligence. Everywhere he postulates the importance of quantum gravitational effects. So today he's again going to tell us about the role of special and general relativity in the collapse of wave function. So I am now requesting Sir Penrose to deliver his IYQ lecture. Thank you.
Roger. Sir Roger.
Hello. Shall I start?
Hello.
Yes.
Yes, so I am now requesting Sir Penrose to deliver his IYQ lecture.
Thank you very much. I appreciate the honor to do this. The title of the talk is The Collapse of the Quantum Wave Function in Influences from Special and General Relativity. Now, I want to start with influences from general relativity. The basic principle of general relativity is the principle of equivalence, which goes way back to Galileo, and he imagined perhaps dropping a big and a small rock, as we see at the top from the Leaning Tower of Pisa, and he argues that they drop together if there were no air resistance. He was well known that if you drop a feather, it would not fall so fast, but that would be the effect of air resistance. If you could remove the air resistance, then they would fall together. As though if an insect sitting on the big rock, looking at the little rock, the rock was seen to hover as though there were no gravity. So you can cancel out gravity locally by falling freely. And in the bottom, we have a sort of futuristic space station and an astronaut there, and the Earth is right there, and the astronaut floats freely, even though the Earth's pulling him. As long as he's in orbit, he doesn't feel the attraction of the Earth. So that's the principle of equivalence. Now, I want to concentrate on that for the moment and consider how that relates to quantum mechanics. And I'm considering how one describes a quantum system which contains, we have a quantum system on the tabletop, and you want to take the Earth's gravitational field into consideration as part of your quantum system. Now, you could do it in two different ways. One is you could simply put a term in your Hamiltonian for the gravitational field. That's the normal way quantum mechanical people would do it. Or you could do it the Einsteinian or Galilean way, which is to say that you imagine that free fall, there is no gravitational field. And so you do the whole thing all over again. So you have the red coordinates and the green coordinates, and the green ones are the free fall ones, and the red ones are the ones where you take the Earth's field as a force. And you go through a calculation, and you find that they're almost the same. The key, of course, is in the almost. The almost is that the wave function, there's an overall factor which isn't the same in either case. You usually say, well, you don't care about the overall factor, that doesn't come into the calculation. But if you look carefully at the overall factor, you see that's an exponential of a thing which involves the cube of the time. It's in green there, you see right in the middle of the slide, t cubed. And this actually means that is there some subtle difference about the two? Well, you see the difference if you imagine there's a large body. So you see at the bottom of the picture, I'm having a large body as part of it. And you want to take into consideration the gravitational field of that body. And that body might be in superposition. So I imagine there's the brown one and the blue one at the bottom of the picture. And they are meant to be in quantum superposition. And you want to do that as well. And the problem there is if you try to take its gravitational field into consideration, it's not constant, and so it's rather hard to do that as you go. And you can't really do it. So what you do is you forget that you're doing it wrong. The correct way would be the principle of equivalence way, so there's no real gravitational field as a force. But if you try to take that point of view, and then when you have this body which is in superposition, the brown and the blue version of it, then your calculation, you say, well, I have to do it the other way, but I make a correction for the fact that I've done it the wrong way. That's roughly speaking what I'm saying. And that little integral at the bottom, I haven't done the details of the calculation. But what you find is that there is a term which suggests that there's a lifetime. Basically, you find that you calculate the error and doing it the wrong way. That is to say, think of gravitation as a force, and then you calculate the error in this, and this error is basically an uncertainty, and the uncertainty gives you a lifetime. It's like an unstable particle. It has an uncertainty in its mass, which is inversely related to its lifetime. So what you say is this superposition of these two bodies has a lifetime, and it becomes one or the other after a certain length of time. Now let me move on to the next slide. The superposition principle is fundamental to quantum mechanics, and normally if you have two states, A and B, then you have any linear combination of A and B, quantum complex linear combination, alpha and beta are complex numbers. It's very remarkable how it all works. Sorry, was there a question, or I'll just continue? Yeah, so that you consider a superposition like this. Now, when you have a gravitational field involved, you have a problem with this. Oh, it's jumped. I hope we have the next. That's the next slide. Yes. Oh, it's jumped. Don't know why it's jumped. Yes, you do a calculation and you find this uncertainty, e.g., which I said is the error or the uncertainty. I consider this is the error or the difference between two states is given by this error. That is to say, if you're trying to make a superposition, then you have to take this into consideration. And what it means, this EG thing shows you it's got a lifetime. And the lifetime of this superposition is the fundamental difference from what would happen in ordinary quantum mechanics. So if you try to take gravity into consideration, you find that the superposition should have a lifetime, and the lifetime is you can describe it as there's some question. Can you hear me, or is there some problem? Anyway.
Yes, we can hear you.
You can hear me. All right. The quantity EG is the uncertainty and its reciprocal to the lifetime of the state. And how do you calculate EG? Where one way is to consider the energy. If it's two stationary states, you have, say, a body in one location or a body in another location, then you consider the and it's a superposition of the two states, one body in one location and the same body in another location. Then to calculate the EG, you calculate the energy it would cost you to move it from, imagine there are two bodies in superposition on top of each other, and you move one away from the other to the location of separation, and you calculate how much energy that would cost you to move one from the other, where you consider only gravitation, no other force whatsoever, only the gravitational force. How much energy would that cost you to pull it away from itself, from the superposition states on top of each other to the displacement of one and the other, and that is the quantity EG. So that's a good way of calculating EG, and the reciprocal of EG gives you the lifetime of the state. So let me move on to the next slide. Now here we have this, we're talking about special relativity now. This is a picture in space-time, and the bottom of the picture you consider a body which is being put into superposition of two locations. So as time develops, the body first of all is in one place, then the dotted part in the middle of the picture is the superposition of the two. The time is going up the picture, I should explain. The dotted part is the dashed part represents the body in a superposition of two locations. And then at the top, you have two locations, Q and Q star, where those are where it gets to when the collapse takes place, and it becomes either the dark spot or the white spot. Now, the problem here is that if it becomes instantaneously either Q star or Q, in the picture that would be horizontal. One of them disappears and the other one is still there. But suppose we look at the picture with respect to an observer who moves very fast in one direction or the other. Then simultaneous is changed, and you have the sloping line either one way or the other, right at the top of the picture. And to an observer moving very fast to the left, this would be the sloping up higher on the right-hand side. If I've got it the right way around, I think so. And that would mean that the one that's for a certain time, you see that the simultaneous line intersects both at once. So you see that when one of them has disappeared, it hasn't disappeared yet. It doesn't make sense, you see. For a certain length of time, they're both there. That doesn't make any sense. Suppose you consider the observer going the other way, then that's the sloping down on the right, left and up on the right. Then it's even more strange. You see that if it's disappeared to be Q star, you find that one of them has disappeared altogether before the other one becomes the whole state, and that doesn't make any sense. So how do you make sense of a picture like this, where the collapse of the wave function takes place at a certain time, and to make relativistic sense? Well, it doesn't make any sense until you go right back to the beginning. So you have to say that the collapse really is referred back to the point where they initially separated. So it was then, in a certain sense, when you have to say the collapse took place, and the branch then decided to be the left one rather than the right one. And even though the time for the decay doesn't take place until they're way up at the top of the picture, you have to say this is referred back to the origin point, and the collapse has really only decided to happen there. It's a very strange picture. Well, let me move on to the next picture, which really goes into this in a little more detail. At the bottom of the picture, you see there is a laser which is firing a photon which hits a half-silvered mirror, a beam splitter, and so that photon is split into two parts, a quantum superposition of going straight ahead, straight along, or being deflected downwards. So you can see this at the bottom of the picture. So the photon goes along, and if it goes along horizontally, it hits that little tiny body, a speck of dust or something like that. It hits the body, and the one that goes down doesn't hit the body. So the body is in a superposition of being hit and not hit. Now we move up the picture to see what happens as time evolves. Time is going up the picture. So we see that the space-time is really in a superposition of being the left hand and the right hand possibility. They're both there at once. The universe is sort of split into two parts for a bit. And it goes on until the wave function collapses, and then it becomes one or the other. And in this picture, I'm supposing that it becomes the one, which is on the left-hand side, and the right-hand side disappears. So the picture is this bifurcating space-time, which becomes separate, a superposition of two space-times, and then after the time has elapsed, when it becomes one or the other, you have to say that all the time it was the left-hand branch. Well, it's a little bit funny to have two different pictures at once at the same time. So the way I say this is there are two kinds of reality. One of them is quantum reality, and the other is classical reality. The quantum reality is the branch on the left-hand side, that classical reality is the one on the left-hand side, which is what the branch always does. And the quantum reality is the superposition of the two. So the quantum reality says you've got left and right at the same time, and the classical reality says that it's got to be on the left-hand side. They really disagree with each other in this picture. But the quantum reality, the quantum superposition persists in quantum reality, and the classical reality, you have to go back to the origin of the point to see how the classical reality evolves, which are a rather strange kind of picture, but somehow the quantum and classical realities diverge from each other. The classical reality is the more robust. The quantum reality, once it's happened, you sort of refer it back to the place where the superposition became one or the other. So let me move on to the next picture, if I have it right here. Let me just see. Yes. Classical and quantum reality. You see, classical reality, you can ask the system, you can say, hello, system, what is your state? And the classical reality has to respond. It says, my state is X, whatever it might be. Now, quantum reality is really very different. You can't ask the system, what is your state? That's not an allowed kind of question. If you try to ask the question, what is your system? It looks at you blankly and says, I don't answer questions like that. Suggest the possibility. And the possibility you suggest, you ask the system, does your state happen to be X, you see? And then if you've got it right, it says, yes, with certainty, the state is X. If you've got it wrong, there'll be probabilities about whether it says it's one way or the other. But the quantum reality may be a superposition between the two, but the classical reality is something which will give you a definite answer to the state, yes, the state is X. Whereas quantum reality will not give you an answer to that question. The kind of question it would give you an answer to is, does your state happen to be X? And then it will say, yes, my state is X with certainty if you have it right. If you don't have it right, or if you have it completely wrong, it will say no with certainty. If you have it sort of in between, then it will say yes or no with a certain probability. So that's the way quantum reality works. Now, I think that may be my last slide, but let me go back to it in a minute because I think it's useful to think in terms of a spin half state. I like to consider, I think I pressed the wrong button. That's why it went wrong, didn't it? I pressed the button on my key. I keep doing that, so I should move it out of the way. I don't know whether I'm even in contact with them.
I don't know where we are, Roger.
Should move that thing way up the picture.
There we are.
Ah, thank you so much. That's what I want. Here's my slide. I hope you can see it and hear me now. Sorry about that. You can hear me, can you?
Yes, we can.
Oh, thank you. Now here we have a space-time picture. This is one I like to use because you can see the discrepancy between quantum reality and classical reality in a very pertinent way. Here I'm imagining, this is the famous EPR type of experiment, and you have Alice and Bob, are two space travelers, and they are handed a spin-half particle, which is split into two. So it starts off as a spin zero state. It splits into two spin half states. Alice is given one of the states. Bob is given the other one. And they are given in a box which you can't get inside at all. It's completely, as long as the box is kept closed, the state is preserved. So each of them has a spin half state, but the state is an entangled state. The total state is spin zero, but each state is spin half. So Alice has a spin half state and Bob has a spin half state. Now they travel off to great distances, light years away, I don't know, great distances apart. And Alice, you can track her world picture as the line going off to the left. And this left goes right up until she opens her box right at the top of the picture. She opens the box and she tries to see whether the spin is up or down. I'm sorry, no, I think it's up to the right or down to the left. That's what she looks at. And she finds the answer is no, it's not that. But nevertheless, it's put into an eigenstate of what she looks in. In other words, it puts into either up to the right or down to the left. I think in this case, it's down to the left. And the point is that Bob's state, since it's entangled with hers, has to be the opposite of what she measures. Now, it has to be a relativistic picture. You have to say that if somebody is looking at the situation with a spaceship moving very fast to the right or to the left, the only way it can be done is to go along the path light cone, and the path light, Bob's state in his box happens to be the opposite of Alice's. That has to be the case. But the quantum reality is in his state is the opposite of what Alice has measured. Now she's measured it to be down to the left. So that means Bob's state is up to the right. And he doesn't know this. He has no idea what she's done. But he makes a measurement which is up-down measurement. And the state that he measures is already, in a certain sense, along the past light cone of Alice's measurement. So you see that diagonal line from her top right-hand point going back down to where it intersects Bob's world line. And that at that point, Bob's state has become the opposite of Alice's. But since it's a quantum reality, Bob has no way of telling what that state is. If he could tell what that state was, you'd be in real trouble. Because you'd be able to send signals faster than light, and you'd be in real trouble with relativity, and the whole relativistic picture would come collapsing to the ground. But fortunately, it doesn't come collapsing to the ground because it's only quantum reality. And Bob cannot ascertain the quantum reality of the state in his box. All he can do is ask a particular question, choosing a direction, and I believe he chooses up and down. He chooses up and down, and he makes a measurement, and it happens to be, I think his answer is yes, that it's up. I think I can't see my picture very well, but I think his one comes up as, yes, it's right, it's up. But that's perfectly consistent. It's just very strange. It's strange because the quantum reality is very strange because it has this retrocausal, in a certain sense, Alice's measurement goes retrocausally back to Bob's point where her past light cone hits his world line to become the opposite of what she sees. But since it's only quantum reality, he has no way of ascertaining what that state is. He can only ask a question of that state, which is his choice of measurement. And then you can see the other side. But when he makes his measurement, then retrocausally, that goes back until it hits Alice's world line. But this is only quantum reality. So Alice has no way of telling what that state is. And so she makes her measurement not knowing that it happens to be already the opposite of Bob's state. So the quantum reality is mapped out in this picture. And you can see it's completely consistent all over the picture, everywhere in all the different regions. I've marked out what the quantum reality of the state is. It's perfectly well defined, and it's retrocausal in certain respects, but nevertheless, it doesn't contradict causality simply because quantum reality is not something that you can ascertain, you can only confirm. You can say to the state, hello state, is your state by any chance X? And the state, if it happens to be X, you can say, well, X with certainty, but is X with certainty. This is a criterion that Einstein put forward. I think people will argue about whether the wave function was real or not. No, of course it's complex, but that's not the point. Is it real in the philosophical sense or not? And Einstein says, well, if you can ask the state with certainty and get the answer with certainty, yes, you got it right, then that gives you an element of reality. So what I'm saying is that element of reality is an element of quantum reality. It's not like classical reality. Quantum reality has this curious feature which it has causal backwards in time sort of aspects to it, but they don't lead to a contradiction simply because it's only quantum reality, which you cannot ascertain. You can only confirm. If you think you know what it is and you have it right, then yes, it says you got it right. But if you don't know the answer, you can't find out what the answer by doing a measurement. You can only confirm reality. You can't ascertain it. And I think that's the last of my slides. So that is the end of my talk. Thank you very much. I don't know if I'm contacting.
So, I mean, thank you very much, Mr. Penrose, for this
Thank you.
talk. So, are there any questions from the audience?
Going to stop sharing.
Hello.
Hello.
Yeah, yes. So I mean,
Can you hear me?
yes, we can hear
Oh,
you.
good. Thank you. Yes.
Thank you. Are there other questions? No. So there's a question. Okay, so I mean, there's an online question that we are just going to.
Okay. No, I'm happy to answer questions. Yes.
What is the question? Yeah, okay. The question is, it seems a key idea is superposition principle. In contrast with quantum theory, however, recently Flemia and Bruckner showed that equivalence principle can be extended consistently into quantum domain. Okay, if you phrase it carefully in terms of quantum reference frame, your thought.
Quantum reference systems.
Yeah, so what it's saying is that Bruckner and collaborators have shown that equivalence principle can be extended consistently into the quantum domain if you phrase
Okay.
it in terms of reference frame. So, do you have any view on it?
I'm not sure I know what the. I'm afraid I'm ignorant of this. Can you explain the idea?
I think this is a question online. So I don't. Who is asking this question?
I mean, quantum reality is very different from classical reality, as I've been trying to indicate.
But in the end, reality has to be quantum, is it, or it can be? I mean, so are there any questions anybody wishes to ask? Okay, I mean, so anybody online? There is no other question. Okay, Sir Penrose. So what is the role of quantum gravity in all this? Is there any role of quantum gravity?
Quantum gravity. Aha. Well, it doesn't answer questions about quantum gravity.
Yes.
I think I should make a point about quantum gravity, however.
Mhm.
You see, people say this is the really important question in physics. How do we quantize gravity and all that sort of thing? Now, of course, that is a problem, and I agree. But the question is wrong. To me, it's the wrong question, because quantum gravity maybe could tell you what happens inside a black hole when the gravitational field enters the singularity, and you might have some way of resolving the singularity, perhaps with quantum gravity or something like that. But that's something which is really so far away from anything that we could actually measure. I mean, if you would have to fall into a black hole to see what your quantum gravity was any use for. I think the right answer is the other way around, which is really what I've been trying to say in this talk. Is how does one gravitize quantum mechanics rather than how does one quantize gravity? See, quantizing gravity is something that would be, well, you might say it had value in the Big Bang. I think actually even there it's the wrong answer. But if you're considering whether you're looking at what's happened inside a black hole, it doesn't help you very much, because the black hole is all inside a horizon and you don't see anything that's going on. However, how do you see how gravity affects quantum mechanics? That's exactly what I've been trying to talk about, because quantum mechanics has a problem, and the problem is the collapse of the wave function. If quantum mechanics was just the Schrödinger equation, or the evolution of the quantum state by something equivalent to that, the quantum evolution, that would be fine. We'd have a consistent theory. But that's not the way the world works. The way the world works is the quantum state collapses from time to time. So we have to understand the collapse of the wave function. And my view is that that is a gravitational effect. So bringing these two great theories together, and yes, I say we must bring these two great theories together, I'm saying it's really the other way around. We're not seeing how quantum theory imposes its will on quantum mechanics, on gravitational theory. Gravitational theory is really what resolves the fundamental difficulties of quantum mechanics, which are already there. They're foundational problems. How do you collapse the wave function? How do you make a measurement in quantum mechanics? Quantum mechanics doesn't hold together consistently without having a theory of measurement. And this measurement theory I'm claiming, needs to involve the gravitational field. And this is the whole key point. Bringing those two great theories together is bringing gravity not bringing gravity under the scope of quantum mechanics, but if you like, giving quantum mechanics under the influence of gravitational. And the gravitational influences are what give us the clue as to how to resolve the problems of quantum mechanics. So I'm taking the problems the other way around from the way people often think of it.
Okay, but can one test if this collapse is due to gravitational effect?
Sorry?
I mean, can one test in lab if this wave function collapse is due to gravitational effect?
Oh, sure. There are experiments. It's very difficult to make a direct experiment. I know in particular of one experiment. This is one being carried out by Yvette Fuentes, where she looks at BECs. These are Bose-Einstein condensates. So you have these liquid helium, and you put the helium into a superposition of two locations, and can you see an indication of the collapse? The trouble is, you see, the collapse would really require you want to keep things isolated. The problem with collapse is that it gets so entangled with the environment that you can't really tell what's going on. So you have to have a system like these BECs, these Bose-Einstein condensates, which are kept very cold And the idea is that you might be able to see an experiment which sees the influence, where really is what we sometimes refer to as the shaking of the building. If the system's getting close to being collapsing, this quantum state is close to being collapsed spontaneous. That is to say, collapse not by somebody coming and making a measurement on the system itself spontaneously collapses. And can you see the effect of it being about to collapse, which is the effect we call the shaking of the building? You can see a term which begins to creep into the calculation, which could actually be measured. Now, these experiments are still a little far from actually being done. You have to think in terms of maybe 5 years from now, but that wouldn't be too bad. As far as I'm concerned, I hope I live long enough, but maybe not. That would be really lovely to see an experiment which sees the collapse of the wave function as an internal effect, not due to, say, getting it mixed up with the external environment, which is what happens normally when you make a crude measurement. Thanks for the question.
So there is another online question. This is about this wave function being epistemic or ontic. So there is a PVR theorem which says that the state about the reality of the state partially by saying that it is not epistemic. Can we somehow connect what you said about the quantum reality to see if quantum state is really ontic? I mean, whether quantum state really exists, I mean, rather than it being epistemic.
You say ontic, you mean, is it sort of real in some sense?
Yeah, yes. So ontic means
yes. Well, I do say it's real, but you have to be careful about quantum real and classical real. They're both real, but they have different qualities. You see, classical real, as I tried to emphasize, is something which you can ascertain directly. So the real, I mean, it's a good argument how real you call that. But the classical real, I think, passes all the tests. You can say you can measure it, you can ask what is your shape, and the system tells you my shape is something or other, and so on. So that is ontically real in the good philosophical sense, if you like. But what I'm saying is quantum real is a more subtle thing. You can only confirm it, you cannot ascertain it. It's real still in a definite sense, but the trouble is that if you're asking it the wrong question, if it's not an eigenstate, if you like, of the question that you're asking it, then it only gives you a probabilistic answer. So you have to be careful about what you mean by real, and saying that quantum real is a different kind of real. It's a weaker kind of real, if you like. But nevertheless, it's a very definite real. But if you know what the state, you think the state ought to be something or other by now, you do a calculation and say, my calculation says the state ought to be something or other, it ought to be X by now. And then you do experiment X on it, and then 100% certainty, repeat the experiment many, many times. Every time it says, yes, my state is X. So that's the kind of quantum real. But if you don't have your view as to what the state is already, and you're just guessing, then you say, well, maybe your state is Y. Does your state happen to be Y? And you have no idea whether it's Y or not. But the state may give you a probabilistic answer. Sometimes it will say, yes, it is Y. Sometimes it will say, no, it is not Y, because you've not chosen an eigenstate of the system. So it's a kind of reality which we're forced to consider when we do quantum mechanics. But I think if you're just a philosopher and you have never heard of quantum mechanics, you'd never think of this idea. Nature is always more subtle than one tends to think ahead of time.
Okay, sir. I mean, there is another question. What is your view on the role of consciousness on the quantum wave function? And do you think consciousness plays a central role in the quantum phenomenon in general?
But my own view about consciousness is it's almost the other way around from what some people think. You see, consciousness is a real phenomenon which happens in the world. Well, we all experience it, so we know we have it. We just have to try and ascertain whether other people have it. Of course, philosophers argue all the time about that kind of thing. But the thing I'm trying to claim is that certainly it's a physical process which produces consciousness. But the arguments I tried to make is that it involves the collapse of the wave function. I think I was thinking about Gödel's theorem and how you understand things, which, etc., etc. I won't go into all that. But the point of view I came to was the argument that classical reality is not sufficient to explain conscious experience. We don't know how to explain it anyway, but that whatever is involved in conscious experience would have to harness in some way the collapse of the wave function. So the wave function collapse, which I'm trying to argue is a real phenomenon, and it's a very strange one, and it needs to be understood if we consider how quantum reality relates to classical reality, the wave function collapse. But whatever is going on in that process of wave function collapse, some deeper theory that we do not yet have, that deeper theory would be needed if we're trying to understand consciousness. I'm not saying I understand about consciousness. I think it's a very difficult question. But whatever is going on would have to involve the collapse of the wave function as part of the process. So this is why I got interested in microtubules and things. I wrote my book, The Emperor's New Mind, really not having any clue as to what could be involved in the brain. And I did learn about the Hodgkin-Huxley nerve transmission theory. And so when I learned about nerve transmission, I really, that doesn't have a hope, because nerve transmission, if you try to preserve quantum coherence, you're in real trouble, because it would perturb or go right through the brain, and the nerve signal would not be isolated enough to preserve quantum coherence. So there's no chance. So you need something deeper than nerve transmission. And when I learned from Stuart Hameroff about microtubules, I thought they were a much better chance. Now, I think we're a long way from an answer even then. I think that microtubules are probably a good possibility for how you might preserve quantum coherence, much better than nerve transmission. Nerve transmission are to transmit big signals and make muscles move this way and that way. But if you're trying to do what thinking is involved with, it may be something much more subtle. And I have no idea really. Certainly there are ideas that Stuart has. I'm no neurophysiologist. I can't really follow to tell you whether he's right or wrong. But if they involve microtubules, which could possibly be in quantum coherence with other microtubules, makes it more plausible as far as I'm concerned. That's the best answer I can give, I'm afraid, to the question.
Okay. Yeah, so you have a question? Yes, there is another question.
Hi, Roger. This is Shivdas. I was the one who actually invited you. So I have a question on when you said instead of quantizing gravity, we can actually gravitize quantum mechanics. So do you think it's possible that quantum mechanics can actually arise from gravity as a consequence of gravity for a certain mass scale, like up to a certain mass, maybe because there's this Schrodinger-Newton equation that you originally conceived, if I'm correct. So there's a paper on Schrodinger-Newton equation where they show that the wave function physically coincides with the mass energy distribution of a quantum particle. So if that is the case, maybe it's possible to get quantum mechanics out of general relativity at a certain limit. What do you think about that?
Well, I don't see how you get it out of general relativity. Well, in particular, general relativity is a theory of real number theory. It's about real space-times, things which don't involve complex numbers. And it's a bit hard for me to see how you would get a theory like quantum mechanics out of general relativity. I don't see that as a serious prospect. It's quantum mechanics is dealing with, it's really, general relativity dominates when you have big things and big masses and so on. And quantum mechanics dominates when you have small things and small masses. They're the different end of the spectrum. Of course, we need to unite all these things, and I certainly agree with that. does need to, but it's uniting them as quantum gravity, I think is perhaps the wrong term. You see, gravity comes in my view, when you deviate from standard quantum mechanics. Well, deviate in the sense that you have to have a role for the actual collapse. I'm not even quite sure. You see, collapse is a bit of a puzzle. If you don't have any collapse of the wave function, then you don't have any measurements, and quantum mechanics doesn't really work properly because you can't even measure it. I mean, there are arguments. Let me not go into that. I don't see how you can base quantum mechanics on general relativity. They're very different theories. You have to have a more overarching theory which encompasses both of them. I think that's what you need. And at one level, at the level of tiny things, you get quantum mechanics, and the level of big things, you get general relativity. But even there are subtleties which we need to worry about, which have to do with the Big Bang. You see, I used to worry a lot about the Big Bang and thinking like other people that it was a quantum phenomenon. Sorry.
What do you think the quantum wave function physically is?
Quantum wave function?
Yeah, is it just a bunch of probabilities as Bond rule says, or is there some physical meaning to the quantum wave function? What do you think it is? Like when you say...
well, it has a reality, but it has a
no,
quantum reality.
No, I'm talking about, oh, is this quantum reality? No, but I'm saying what physically it is. Like, is it some, for example, there is this paper from Angelo Vassi's group on Schrodinger-Newton equation, as I said, that they sort of say that the quantum wave function coincides with the mass-energy distribution of the quantum particle. So, what do you think about that? And I mean, I'm just thinking that what your thoughts are about what a quantum wave function physically is. Is it just a bunch of probabilities, as Bond's rule says, or is there a deeper physical meaning to it?
Well, is the quantum state, does it have is that a question? Does it have a reality in some sense? I mean, yes, it does, but I'm not completely sure I understand the question. I am trying to say that there is a quantum reality, yeah. But you have to see that it's not the same as the classical reality. They interplay with each other, but you have, and the actual reality involves both. Actual physical reality, if you like, involves both the quantum reality and the classical reality. So they're part of different parts of the whole story, if you like. But the quantum reality doesn't go very far when we're considering gravity. But gravity comes in when the measurement process happens in, I think, you see, all I can express is the kind of view I have. I don't see quite how it relates to the question. I think I'm a little bit confused by the question. We don't.
Yeah, there is another question. How do you reconcile quantum non-demolition measurements with collapse of wave function?
You see, observation.
Yeah, non-demolition measurement. How we reconcile them with collapse of wave function?
Well, I'm still not quite. See, observation, in my sense, is a rather bad word for. I mean, it's what people use when you reduce the quantum state, the collapse of the wave function, and they say you observe the quantum state, but it's not really to do with somebody coming along and observing it. That's a view that I think some people hold, that somehow it's the conscious observer looking at the state, which somehow collapses the wave function. That's certainly not my view. The collapse of the wave function is a physical process, and a conscious observer has nothing to do with it. I mean, the conscious observer, it's another question.
No,
can you
Roger,
explain
the
conscious experience in some way? But I'm saying that a conscious observer is certainly not necessary for the collapse of the wave function. That's a physical process which happens whether there are conscious beings around or not. It doesn't care anything about the conscious beings. That's not an important aspect of the collapse of the wave function, in my view.
Actually, the question was about quantum non-demolition.
Oh yeah, you will have quantum states which are keep
Yeah,
them going very well, and the quantum non-demolition. That's probably, I mean, it's not my area, but you can certainly preserve quantum states. Sure, there's nothing wrong with that, as long as they don't move too much mass around. If these quantum states were to move much mass around, then they would collapse, and the quantum state would not be preserved. So I take the idea that when you preserve big quantum states, in the sense you are not moving very much mass around. If you were, you would lose it. So it's provided these are very, very low in actual mass, or mass displacements, if you like. The whole thing can have a mass as long as you're not concerned with quantum displacements of mass. Then you would be in trouble, because the quantum displacements of big masses would result in the reduction of the state, or the collapse of the wave function. So that's what I'm trying to say, is the collapse of the wave function comes about when too much mass is moved around, if you like. You move it around and try to keep the superpositions going, then you're in trouble. It may well collapse on you. So I don't know if that's any answer to your question, but it's sort of expressing my viewpoint.
Okay. So I think there
Sir, I wanted to ask about the last picture that you presented regarding the entanglement between Alice and Bob. And in the world line of Alice did a measurement at a point MA, and
Yes.
it retrocausally affected the world line of Bob at a point QB. And there is still some time between the measurement made by Bob, as it happens sometime later at the point MB. So there is
It could be earlier. Yes.
So there
In
is
some frame of reference, it might be earlier than Alice's measurement.
Yeah.
That's the thing.
There is a possibility that after the point QB in some reference frame, the system evolves into another superposition state until Bob measures it. So the quantum reality can emerge again. So can you comment on this? And
Bob's measurement changes the quantum state. So it would have been the opposite of what Alice's measurement had produced in it. And this could be retrocausally, and this depends on your frame of reference, you see, whether it's before or after Alice, as long as it's not before the past light cone of Alice. If it's before the past light cone of Alice, then it's still even quantum unknown. But once you get beyond the past light cone of Alice, its quantum state has become the opposite of what Alice measures. But since it's only quantum reality, it's no contradiction, because Bob has not performed a measurement on the system until he actually measures it. And then he disturbs the quantum system that becomes the classical reality that he measures. And sure, that's all right. But that can be, in some frame of reference, that can be before Alice's measurement. So you have to, that's why, that's the puzzle presented by my picture. As you see the past light cone of Alice, he can't get before the past light cone of Alice when she makes her measurement, but he's after that past light cone. And this means that the quantum reality of his state is already determined by the result of Alice's measurement. So which is very peculiar, because it seems to be retrocausal. It goes back in time. But since it's only quantum reality, going back in time does not cause a contradiction, because Bob cannot ascertain the state of his particle. You can only measure it, and that may spoil the quantum state. I'm not sure that's anything to do with your question, but I'm repeating basically what my picture says.
There is another question which relates to mathematical structures that were introduced, I think, by you in connection with quasi-crystals. The question is, what is the role of this mathematical structure in understanding quantum decoherence in curved space-time, especially when you have gravitational waves, moving around?
Oh dear, I've forgotten what I did I? Perhaps you could repeat the question because I didn't quite understand.
Okay, so I think there was a mathematical structure that were introduced, which relate to quasi-crystals. Now, question:
Yes.
how these mathematical structures inform models of quantum decoherence in curved spacetime? So, those mathematical structures, can they play any role in understanding quantum decoherence in curved spacetime?
In understanding quantum reality, quantum, well, I missed the word there.
Basically,
In
how
under,
to question is about quantum decoherence in curved spacetime. I mean, what kind of mathematical structures can help us in understanding this?
something going beyond current quantum mechanics?
No, no. Basically, you have this some. So the issue is about mathematical structures that may be required to understand quantum decoherence in curved spacetime. I mean,
Yes, so we understand quantum coherence
yeah, in curved spacetime.
in
Curved spacetime. I mean, when we have, spacetime is curved.
space-time.
Yeah.
I don't see any contradiction with space-time. I mean, my picture with Alice and Bob was a space-time picture. So it's perfectly consistent. It's just that you have to make your quantum reality, your classical reality, quantum reality pictures. The quantum reality may not be global in the whole picture. You see, in certain regions, you have certain quantum realities, which I tried to indicate in that particular last slide, which I had. So you have Alice and Bob in a space-time picture, and you consider at each point what is the quantum reality of the state, and it seems to make a consistent picture. I've never looked at it for, say, 3 observers, and it would be an interesting exercise. Is it still true that you have Alice, Bob, and Fred or somebody, and you've got 3 people, and they are making their measurements at different times, and you look at the retrocausal aspect of it and all that? Does the quantum reality of the picture still make sense? And that would be a good exercise for somebody. I only looked at it for the Alice and Bob with just 2 people, and whether you can continue that analysis to see whether the quantum reality makes global sense for 3 people would be an interesting exercise. I don't expect it to be different, but it might be. That would be worth looking at. I'm not sure it's an answer to your question, but I think that is the sort of thing. I mean, I'm trying to, in that picture I gave you in the last slide, it really is a space-time picture. So I'm looking at space-time, and I'm trying to see how quantum reality relates to the entire space-time. And yes, it does, and it seems to be consistent. It's causally quite strange because you see Alice's measurement seems to be retrocausal. It seems to go back along her path light cone to see where it intersects Bob's world line, but nevertheless, it gives you a consistent quantum reality to the whole picture. So that, all I'm saying is that as far as I've taken it, and maybe somebody could go further with this, as far as I've taken it, I see no inconsistency between the quantum reality picture and space-time picture. Space-time still works. Now, it may be that if you want the measurement in there, as I was trying to do in my, I think, not quite the last, not quite the last slide, but the one before the last slide, I was showing you space-times, which seem to be bifurcating, and you have the quantum picture and the classical picture, which are not quite the same. And maybe when you bring that into it, there can be some curiosities about how the space-time relates to the quantum picture. That's quite possible. It would be a nice exercise to try and do that. I haven't done it any further, that I showed you in the pictures today.
Okay, so if are there any more questions? No. Okay, so since there are no more questions, so I think let's all thank for Penrose for this very interesting talk.
Okay, thank you very much.
Okay, so I mean, thank you very much, Sir Penrose, for giving this talk. Thank you very much.